Okay, it's just gone 1 o'clock, so I think let's start, and I'm sure people will still filter in over the next few minutes, but let's get going. So, hi, I am Rosie. I'm the Communications Officer for the Department of Mechanical Engineering here at UCL, and welcome to Computational Modelling, the Heart of the Matter, a talk by Yiannis Ventikos, who is also our head of department. Before we move into Yiannis's talk, there's just a couple of housekeeping things that I'm just going to quickly run through. So this talk is part of Spring into STEM, which is a series of talks hosted by the UCL Faculty of Engineering. So do take a look at everything else on offer. We've got a couple more coming up as well as part of mechanical engineering, so do look at those. I'll pop a link in the chat at the end of this talk as well. For this talk, it is being recorded, so it will go up online at a later date, but because of that, we won't be asking participants to use their mics or put their video on at any point. If you want to ask a question, there'll be a Q&A at the end. So for any questions, put that in the Q&A box, try and keep it in there. If you have any issues, so you're worried that you can't hear or anything else, pop that in the chat and we'll answer that as we go. We'll get to the questions at the end as well, so we'll leave the Q&A to the end. And that is about it for housekeeping. So I will now pass you over into the very capable hands of Professor Yiannis Ventikos to start his talk.
Thank you, Rosie. What I'm trying to do now is share my screen. And I hope that everybody can see my screen, right? Okay, so this is a talk about computational modeling, and I want to thank everybody for being here today. This is a topic that is a bit out of the ordinary as far as especially the second part of the title, the heart of the matter, and I will explain why we, as mechanical engineers, have something to say about hearts and diseases and healthcare overall. So this is a very quick slide regarding who I am. So my name is Yiannis, as Rosie said. I am a professor in mechanical engineering at UCL, and I'm also the head of department. And if you look at the various places that I've been in, the various types of departments or academic institutions that I have existed in academically, you'll see that it's pretty much all engineering. So the question would emerge: what is an engineer doing, talking to you about healthcare? And the answer to that is that there is a lot of engineering in healthcare, in medicine. There is a lot of engineering in treating patients, call it whatever you want, from stuff that we all know, like scanners, MRI scanners and CT scanners, all the way to machines that actually do things to our body that change the composition of our blood, to very complicated robotic systems for surgery, to things that we put inside our body, implants, as they are called, that treat difficult conditions. They all have to do with engineering. So basically, the pattern of operation here is that there is usually a clinical need, a medical need. We call them unmet needs. And through an engineering solution, we hope to result in improvement for patients. And in this respect, my talk will try to capture as much of this pipeline, of this ecosystem as possible. This is a picture I very much like to show. This is UCL in the evening, and what you see at the front is the main building of our university, but the tall building you see at the back, the big tall building with a green building with the lights, that is one of the world famous UCL hospitals, the hospitals that are connected to our university, that make working in healthcare, in medical problems, if you are a medic or if you are an engineer, really relevant, really important. And the building, of course, you see at the back is the main UCL hospital, but there are many other hospitals in UCL that are, world famous, like the Great Ormond Street, the Children's Hospital. Now, in our department, we do a lot of bioengineering, and we have a lot of things to show. I will not discuss any of the very broad range of things that we've done, but I will say a word about the thing that you see at the top left here. This is the UCL Ventura. Now, with the COVID crisis, our department, our university, our department, as a matter of fact, was one of the very few that came forward and addressed a real need that hospitals have, which is for ventilators, for non-invasive ventilators, as a matter of fact. So our department, in record time, basically produced this little device that you see there that gets oxygen from the supply of the hospital and increases its pressure and puts it on a mask at the face of the patient. We designed, built, tested, got an approval, and started distributing this device in record time, literally in weeks versus years that it usually takes. And we sent 10,000 units to all hospitals around the country, and the design everywhere in the world of this device. I have to say, together with the Mercedes Formula One team, a longtime partner of ours. I will discuss, I won't be discussing COVID, but I will be discussing one particular type of work that we do that is called computational modeling, and I couldn't resist the temptation to show what computational modeling can do in a COVID setting. So this is someone sneezing on someone else's face, and what you see is the difference between sneezing at someone's face with or without a mask visor system that we didn't have to do any real experiments. We could get this kind of result and this kind of comparison using computational modeling. The topic I will talk about, however, is how we can utilize this kind of thinking and put it in really good practice from a university all the way to patient healthcare. I showed you this diagram before, and in reality, the bit that is at the focus of what we do is this box, which gives rise, opens up a rather complicated ecosystem of research and commercialization. And I said complicated because there are a lot of things happening, a lot of things need to happen in order for an idea or the product of a collaboration with an engineering and a medical team to be transferred into a final product that reaches the patient. It involves academic research, it involves student projects quite often, and even undergraduate projects. It is quite common for undergraduates to be embedded into this type of work in different labs around the university. It involves things that you would expect, like publications, presentations, and conferences, but it also involves ideas, inventions, patents, licensing, companies. All this requires money, but the end product is something that you may build and use in a hospital in order to save lives. The environment that, the topic rather, that I'm going to apply this kind of thinking is a broad thing that we call cardiovascular diseases. So cardiovascular diseases is all the things that we quite often, unfortunately, hear about: heart attacks, strokes, vascular disease, deep vein thrombosis, etc. It remains, and if anything, the situation is worsening, actually, the biggest killer in the world, definitely the biggest killer in the Western world, whatever that means. But even countries that didn't have a high prevalence of cardiovascular disease now are developing a high prevalence of cardiovascular disease, like, for example, China, that I know a lot about. There are many different types of disease of the heart, disease of the brain, the disease of the vasculature or the muscle of the heart, etc. What I'm going to focus, the bit I'm going to talk about and use as an example, as a template, because we've done a lot of work on this topic, is one particular type of stroke. It's called hemorrhagic, which means bleeding. And basically it means that something breaks in the vasculature of the brain and you get blood leaking out. And usually what breaks is something that's called an aneurysm. So what is an aneurysm? An aneurysm in the brain, or cerebral aneurysm, is a ballooning of a blood vessel, like you see in the picture there. Now, this is really important for a variety of reasons. The most important reason is that the brain is a very hungry organ in terms of food, and by food I mean sugars, and also oxygen. The brain has no capacity to store oxygen. So if the supply goes down, even for a little while, even for a minute or two, the brain starts suffering. And not only that, it has no reserve. It cannot store blood or oxygen. It uses whatever comes in all the time. It has a very high demand. So the brain, even at rest, even we are not doing anything, we are sleeping or looking at the wall or something, it requires a lot of blood, a lot of oxygen in order to keep healthy and to operate. It requires roughly 10 times more blood than each weight would imply in the body. So it's really, really hungry organ. And of course, if something happens that disrupts that supply of blood, it's serious business. And aneurysms through bleeding actually do that disruption. So what you see on the left, on the right here, is a post-mortem of an aneurysm. I apologize if some of you find this a disturbing picture. It's basically a giant aneurysm that has ruptured, and then they have extracted the vessels. And what you see on the left, which I may be able to stop, is this thing up here. This is how an aneurysm looks at a particular type of X-ray, this object on the top curve of this vessel. So why are they bad? They are bad because they occur to many people, to roughly 5% of the general population. So in any group of 20 people, one of us is going to develop an aneurysm at some point in their lives. But this is not necessarily bad news because very few rupture. So maybe 1 in 100 aneurysms, or 1 in 1,000, depending on the study, rupture. So most people that develop an aneurysm will have that aneurysm in their head all their lives without knowing, without any problem. When they do rupture, however, they are bad news. They have very high mortality, which means that if an aneurysm is detected, you go to the hospital for some other reason, and you have a headache, and you get your head scanned, and they find an aneurysm. Usually, in most cases, the doctors have to do something about it. So this is how aneurysms were treated in the past. This is a way to treat aneurysms, which involves, it's called surgical clipping, and involves surgery. This means that you have to cut the skull open, go in and put that clip that you see over there to isolate the balloon, which is the soft, sensitive, prone to breaking part, from the main circulation of the blood. So whatever happens to the balloon after it has clipped, you don't care. It has been isolated from the blood. Recently, in the past 20 or 25 years, there was a new treatment that is called coiling. So coiling basically means that you stuff the aneurysm, this balloon, with a catheter that you guide through the body, with a little, very thin platinum wire. And what that wire does is basically it makes the flow inside the aneurysm very slow. And if this happens by creating this porous medium inside the aneurysm, the blood will probably become stagnant and clot. And if it clots, it means that there will be no new blood coming inside the aneurysm. So the aneurysm will not break, will not start leaking blood. This is a process called thrombosis, and when it works fine, and in many cases it works just fine, the aneurysm is deemed cured. This little video here shows live from the interventional suite in a hospital the process of guiding a wire. You see the little black thing that moves inside the vasculature, and now it has reached the aneurysm. So the wire that the surgeon is using to navigate has reached the aneurysm, which then has a tube going over it, and that tube starts, through that tube, you start pushing those coils inside the aneurysm, and you create this multiple loop. So this is the process of aneurysm coiling, which is the main treatment these days, I have to say. The downside of this is that you are putting something, a very flimsy, but still a wire inside the most sensitive part of your vasculature, which is this very thin aneurysm wall. So the idea was, can we do something to avoid that? And there is a new technology now that's being pushed, and it's increasing usage. We are saying that's called flow diverters. So a flow diverter is like a grid, like a mesh that you put it inside the vessel, and it has each action is again to create thrombosis inside the aneurysm. We're going to see how this is done. The advantage of this is that you put nothing inside the aneurysm dome, inside the aneurysm, the weakened, the soft and vulnerable to rupture balloon of the aneurysm, okay? So the first thing that we need to do in order to figure out how to treat an aneurysm is to position the flow diverter. So this tool that you are seeing here, this little video, is a company that is operating out of London these days that emerged from research done within the university that grabs the image from the CT scanner or the MRI scanner, creates a virtual environment in the computer, and allows the doctor to start playing with the positioning of this flow diverter. So this is a very important step because the doctor now can see, do I need a longer one, a shorter one? If I put it through this branch, through the other branch, where is it going to sit exactly? Very important. The second, even more important step, however, is this, is the step that says, once I have positioned the flow diverter, and this is one of my most important slides, what will it do to the blood flow? Will it create enough change in the blood flow, enough change in the hemodynamics in the brain in order to lead to this slowing of the flow of blood inside the aneurysm and therefore to thrombosis, to stagnation, to treatment of the aneurysm? So you put that grid over the opening, over the neck of the aneurysm. On the left, the video that's playing here, you can see how the aneurysm looks and how the flow in the aneurysm looks before you put the flow diverter. And you can see that inside the aneurysm, you get a lot of flow, a lot of vortices. The pink colors here means high velocity blood. So this is blood that is very actively flowing inside the aneurysm sac. It may be putting pressure on the wall. If it ruptures, if the aneurysm ruptures, it means that you have a huge supply of blood for it to leak out. All bad news. The picture on the right, you can see that the flow diverter has been positioned now. It is in place. And you can see immediately from the streamlines, from the lines of flow inside the sac of the aneurysm, inside the balloon, that there are a lot less of those lines, which means that a lot less flow is going in the sac. Less flow means slower velocity. So this is qualitatively a very good picture. This flow diverter would reduce the flow of blood in the aneurysm, right? I'm going to just say a word, a single slide, about how we do that. So the way we do that is that we solve on the computer some very complicated equations that govern the fluid flow. At the top line here, the top equation is one of those equations, which describes the change of momentum of the fluid in the x direction. However, those of you that may take a look through the mathematics, you're going to realize that the only thing this equation says is that change of momentum is equal to forces. That's what it says. You know, on the right-hand side, we only have forces, which is a very sophisticated, very relevant way to just express Newton's second law that you know a lot about, F equals ma. It is written in a differential form, as it's known, because it's helpful to write it that way if you have complex vessels that change with complicated geometries that you need to cut down in little boxes like I have shown in the bottom to create a mesh, as it's called, because that's how we solve those equations. But the essence of what we are solving is nothing but Newton's second law. With very sophisticated tools, we can solve that and get velocity and pressure fields at the end of the day, which are my variables that tell me how the flow behaves in these very complicated geometric entities, that is the brain arteries, with and without devices, with and without flow diverters. And if you can do that, then you have a full description of the flow inside the vessel. And if you have a full description, then it's really only a matter of graphics, realistically, of computer science, to position yourself wherever you want. And what I'm doing here is I am positioning myself inside the vessel, inside the artery. And I am looking at how the flow goes inside this artery by plotting some vectors that are the little arrows that you see, three-dimensional arrows that you see all around. So this is something that we call virtual endoscopy, because endoscopy means looking from the inside. Virtual, because I don't need to stick a catheter there. I can do that just by using the computational modeling information I have already. Now, you can test this. You can test the performance, if you wish, of this aneurysm in real with the existing devices. And what I'm doing here is I'm testing some devices that already exist in the market that are being implanted in patients all the time. The one on the left is called the silk device. And what I'm testing here is whether I can place the silk on the left-hand side, on the left branch of this aneurysm, or the right branch. On the right-hand side, I have another device that's called the web device that puts basically a grid type ball sphere inside the aneurysm. They both do the same thing. They create a mesh, a grid across the neck of the aneurysm to reduce flow. And if I can do that, I can also do, of course, new devices. This is a device that was developed in Canada with a group that we work with, and it's called the Eclipse device that, again, puts a mesh of a different type at the neck of the aneurysm. This is another device that's called the Sphere. It's developed by a company in New York. Again, we're working with them. We do their analysis. That is basically a very long shape memory alloy wire that you put in the aneurysm neck, and then this, as if by magic, remembers its old configuration and again creates a mesh at the aneurysm. If I can do all that, then I can start creating some real value for the interventionist, for the doctor that will have to make a decision on how they're going to treat a particular aneurysm. So what I can do is I can examine the hemodynamics, the flow of blood in this aneurysm, this particular aneurysm, which is one particular patient that we had some time ago, with all the devices that I have at my disposal. In this case, I have the first device that I call the silk, that I can put either on the right branch or the left branch, as you can see. I can have the web device that I have at the top right there, and I have the two new devices, the Sphere and the Eclipse. And I can do the computations that I mentioned, and I can create a comparison based on some quantity that I think is of interest. In this case, the quantity that I chose that is of interest is to compare how the percentage of the reduction of flow inside the aneurysm. So I have the left picture with no device. All the flow goes into the aneurysm. Let's say that's 100%. If I put a device and half of that flow now doesn't go into the aneurysm, then I say that this device introduces a reduction in inflow of 50%. And ideally, I would like to have a reduction of inflow of 100%. So no flow at all goes in the aneurysm. But of course, that's impossible to achieve. The truth of the matter is that even reductions of 40 or 50% are big enough to create enough stagnation, enough reduction of blood flow in order to for for thrombus to form and for the aneurysm to be treated. Now, this is very useful, but what is even more useful is this. And this is my most important slide. This is my most important result at the end of the day. And this is the last thing I'm going to show you, as a matter of fact. So this is the same results that I had in the previous slide, only quantitative. So I am actually calculating how many milliliters per second of blood go into the aneurysm without the device and with the various devices, and I compare. The higher you are in the bar here, the better. So I can see some very interesting things here. So one of the existing devices does really well. The web device here does like 70%. By the way, I'm not testing the real device. I'm just, putting this as a disclaimer. I'm testing a device that looks very much like it. It's almost identical. I don't want to infringe on any intellectual property issues or stuff like that. I'm just doing an academic study here. However, the kind of insight that I'm getting is quite revealing. The web device does 70% reduction. There is a huge difference. That's another interesting result. The two bars on the left is the same device, is the same, like a tube made out of that grid. And the only difference is that I take this same tube and I put it on the right, or I put it on the left. And you can see that the difference between those two is quite dramatic. In one case, you get a performance that's 50% reduction, which is probably perfect. The aneurysm would be treated and cured with 50%. And if you choose the wrong branch, if you put it on the right, you only get 30% reduction. So 70% of the blood still goes into the aneurysm. That's probably not good. So this is already very interesting to the interventionist, to know that if you decide for whatever reason to implant the silk device, put it on the left branch because it makes a big difference. And the new devices, the Eclipse and the Sphere device, they both do reasonably well, not as well as the web, but they do between 40 and 50%, even above 50%, which means that if those devices could actually get there easier, which they do because they are thinner, right? Then it may be that there are aneurysms where you cannot implant the very best device in terms of performance because it's too big. So you go to one of those devices, the newer ones, and you know that you're still going to get enough performance. So this is a really valuable set of information, a really valuable group of advice that you can give to the interventionists regarding how this is going to work. And we've done this kind of study, not just for one or two, but for dozens of aneurysms in order to create some interesting statistics, etc. So let me wrap up. I think I've done a full half hour. Computer modeling of the type I'm describing offers insight that you probably cannot get through any other means, and allows you to quantify, basically allows you to predict the future. It allows you to say that this device is going to work, this device is not going to work, which is really useful for interventional medicine. The process, everything I have described here, no harm to animals, no human subjects involved. It is all done virtually on the computer. So this is very appealing. It's for ethical reasons, for cost reasons, and it's perfectly repeatable. If I run the same simulation of the same patient data 100 times, I'm going to get the same result 100 times, right? And finally, you get some very fancy, very cool animations, which is something I also like very much. And it is not just the animation, it is a way to communicate very difficult, very complicated results to a broad and wide audience. So with this, I'm going to stop. I'm going to thank you for your attention. And if you don't mind, I will stop sharing my screen in case we have some questions.
So we've had a couple of questions come through.
Yep.
Yep.
So should I go to the chat now?
Yes, that would be great.
Okay, so let me start from the beginning. Does it have any risks? For instance, would the flow diverters clot and stop the blood flowing? It's not stupid. It's a very good question. So the flow diverters and everything you do in the vasculature is sitting on a very fine balance. You want clotting to happen inside the aneurysm. You do not, of course, want clotting to happen inside the main vessel. So if you can control things perfectly and you introduce this reduction in blood flow inside the aneurysm, and you keep a very, it's called patent blood flow in the main vessel, that's perfect. There are two ways that things can go wrong. One way is that you get reduction of flow and clotting inside the main vessel, and this is very bad. You're absolutely right. I think it was you, Ziching, that answered that question. So in order to avoid that, we try to err in the other direction. We try to make sure that there is no clotting in the main vessel. In that case, the risk may be that you don't have enough clotting inside the aneurysm, which means that you may not be treating the aneurysm. And this does happen actually. And this is why these tools are really useful, because they can tell you beforehand that, this particular device, if you put it like in that particular location, has a very good chance to introduce the right level of clotting inside the aneurysm and no clotting on the outside. Okay, is it possible to rewatch the meeting later? Yeah, of course. I think you can get it from the recorded session. And do the flow diverters have any risk as far as clotting? Now, this question was answered, but I want to expand the answer just a bit. The flow diverters have very reduced, risk as far as clotting. What you need to happen when the aneurysm is treated, is considered fully treated, is that you put the flow diverter, the flow inside the aneurysm becomes so slow, the aneurysm fills with clot all the way to the flow diverter, and the flow diverter and the clot have a surface. And if that happens and it's stable enough, then you get the growth of a particular type of cells on this surface. So the entirety of the inside of the vessel has the same covering of those cells. These are called the endothelial cells, and they have to be, it is the healthy lining, if I can put it like that, of the inside of vessels. So an aneurysm is deemed perfectly treated if the flow diverter has been covered completely with that lining of endothelial cells, which means that the blood that's flowing in the vessel does not know that behind this part of the wall there used to be a balloon, and behind this wall there is now a grid of metal because it has been covered with endothelia. So the real risk is that what I described does not happen. Sometimes the clotting in the aneurysm is not good enough. You still have some inflow, outflow, and you don't get this lining to happen. And this is what we are trying to avoid. This is what we are trying to eliminate. Does your research group consist of multidisciplinary researchers? If so, what contributions can bioscientists and biomedical researchers make to this type of research? So that's a very good question. We try to collaborate. We try to bring inside the group people of a variety of disciplines. And because we cannot have absolutely everybody inside the group, we also collaborate with people across the board, from biologists, biochemists, medical scientists, etc. An aspect that I did not speak at all about because I didn't have time, and I expect that someone may have that question at the back of their heads, is Yiannis, you talked a lot about thrombosis. What about thrombosis? So the truth of the matter is that we can model thrombosis too. You don't just have to model flow of blood. You can actually model on the computer the growth of this clot type material inside the aneurysm. And this is a very, very strongly biochemical problem, right? It is a whole bunch of biophysical, biochemical reactions that interact with each other, with factor this, factor that, platelets, agents inside the body. So it becomes very interesting in this aspect. Biomedical and biochemists, bioscientists, etc., have a lot to say on this domain. How do doctors choose which device to use to reduce blood flow in the aneurysm? It's a very good question. So far, the choice has been on experience alone. So basically, the doctors have treated their brains, their heads, as an expert system, as a machine learning system, and they have been reading papers, they have been integrating information, they have been seeing what their colleagues are doing. They are getting this aneurysm that looks like this. I treated this 3 years ago with this device and it went well. Or my friend in, I don't know, in Shanghai or in Toronto treated it with that device and it went well, or it treated it with the other device, it didn't go well. So they did that through experience. More and more these days, doctors are using tools like the ones I am describing. They have not been generalized. We are at the phase where new tools are being developed and they are fighting for market share. My prediction is that within the next 10, 15 years, it will be out of the question to do an intervention of this type without having solid simulation results. So we're at a point where the tide is shifting, if I can put it like that. Will the flow diverter last forever, or do they need to be replaced? Very good question. So theoretically, if everything goes well, the flow diverter is going to be hidden behind that layer of cells that I said. It stays there forever, doesn't need to be replaced, it's fine. There are other devices that go to other parts of the body that have been made of biodegradable materials, so materials that are very intact and separate when you implant them, but with time, they become thinner and flimsier and eventually they get absorbed by the body. This was something that was a big trend for coronary interventional implants, for coronary stents. They don't seem to be working so well, so I don't know what to say. In general, you shouldn't depend on a device stopping to exist. I think that's my own personal view. You should try to implant devices that you are happy if they stay there forever, they're going to be doing their job. And this is the case for flow diverters right now. In this specific field, how do you make sure that the simulation results are representative of reality? Excellent. What are the most used techniques for correlation? So there are 2 or 3 layers. We call this process validation and verification. So if you don't mind, just for this question, I might share one more slide. So what you're seeing here is a different piece of vasculature. We did the simulation. The simulation is at the top left. But then we did an experiment. So we build using very sophisticated 3D printers an exact replica of the piece of vasculature that we wanted to test. We put it in a fluid loop, and you see that on the middle right. And we use the laser technique, and the pink color that you see there is the color of the laser that creates a sheet inside the material, and you take measurements. So you measure how the flow looks, and you compare your simulation with the measurement. If you see the picture at the bottom right of this, which is a quantitative measurement, we are happy that the result is perfect, is one on top of the other. So there is a lot of work that we can, should, and are doing regarding this validation and verification. That was a very good question. Is there a risk using computer model based on simulation that can depend on circumstances that change from time to time? Again, very good question. Thanks, guys. This is excellent. It means that you really understand what is the issue. And the answer, of course, is yes. So I am rather relaxed now. I am having, maybe 60 beats per minute in my heart. My blood pressure is normal. Things go in my blood flow the way they do. If I go out and run for 5 miles, if I could run for 5 miles, and I get my heart rate up a lot, or if I have a big meal, which is very spicy, and again, my hemodynamics are going to change completely. So there are ways that we are looking into that, and we did a paper some time ago, actually, where we compared hemodynamics. Other people have done that too, compared hemodynamics between normal rest conditions and some very extreme exercise conditions. But the situation does indeed change, and in reality, if you want to be comprehensive, you must scan a range of conditions for each case. Can computer modeling be used in real time, say in a general medical procedure, to aid doctors directly? So in the type of modeling that I showed, there were two components. One component was the deployment of the stent, to put the stent, the flow diverter in the right position. And the second component is, once you have the position, to see what it does for flow, for the hemodynamics. The first bit, if you are to do it with normal, let me call it like that, normal engineering techniques, takes hours to find exactly, to put the position and say, now open the stent, and the stent opens and start pushing the walls and everything. We and others have developed some very smart algorithms where you lose a bit of accuracy and you gain immensely in terms of speed. So something that would take hours on a normal computing environment with normal software, with this kind of software that I'm talking about, takes seconds. So it's almost real time. So that aspect, you can do real time during surgery. So before the surgeon actually presses the button to deploy, he can have the computer on the side and say, okay, I have put it there, press on the computer, this is how it's going to deploy. He gets that result in a couple of seconds. So that side, very good question, it has worked. The other side, which is, can you compute the hemodynamics? Can you compute the flow fast enough? For the time being, the answer is no. For the time being, even with the biggest computers, this would take tens of minutes. On your laptop or on your desktop, it would take a couple of days for a simulation like this, for a single simulation. You usually want to do more. So is a few minutes, is like 10 minutes too bad? In order to get 10 minutes, it means that from your computer, you connect to a supercomputer somewhere, and when you press the button, a lot of things happen automatically, and the computational task goes to the supercomputer, computes parallel, many cores, many parallel processes, and then comes back all automatically and shows you the results. This can be done. It is still a few minutes, it's still, let's say, order of 10, 20 minutes, with hundreds, let's say, of course, so really big computers. And if you want to compare like 10 scenarios, it means that you need to compute simultaneously 10 of those cases. So for the time being, if you had a gigantic computer available to you, you could do that within an hour, let's say, but not real time. I think that in the future, we're going to go there more vigorously, let's put it. Is there a risk of blood vessels being ruptured when they pass through the mesh before an endothelial tissue is formed? So they don't pass through the mesh. The mesh actually sits on the inside, or if it's a coil, it sits on the inside, but it's a very good question. And the answer is yes. There is a risk to rupture the vessel, either because of the mesh of the flow diverter, or more usually because of the catheter, the guide wire, the bit that you go in from the leg and you drive the catheter all the way up through the carotid and you reach the point in the brain where you want to deliver. And there is a risk. Yeah, there is a risk. There is, this is not a statistic that is very commonplace to be reported, but there is around 1 in a million iatrogenic, it's called. It means iatrogenic means caused by the doctor, literally. Iatrogenic deaths reported for endovascular interventions in the brain. And this is only the cases that are being reported from the very best centers around the world, the ones that dare report this kind of result. My suspicion is that the numbers are greater, and it's not just bad manipulation of the catheter. Sometimes you might be doing everything right, might be the most experienced person in the world, and because that person has the patient has some weird corner somewhere, the catheter gets stuck and you are in very hot waters. I have seen this kind of cases happen in the hospital. They are not pleasant. So the quick answer is yes, it can happen. It's very low prevalence, and we are getting better all the time. I mean, that's the only thing I can say. Is computational modeling an expensive process? So it is expensive to develop the codes. Once you have the codes, the only cost is the computer, so to speak. And as I said, the deployment algorithms right now will run very comfortably on any laptop. I would say that even my mobile is powerful enough, my phone is powerful enough to run the deployment algorithms. For the hemodynamics, for the computation of blood flow, if you are in a hurry, if you want to do it in 10 minutes, let's say, then you need 1,000 cores. You need a computer, a cluster with 1,000 cores. 1,000 cores is expensive. It's going to be in the, let's say, 30, 40, 50,000 pounds for the entire infrastructure. Of course, if you think about expenditure in a real hospital today, 50,000 pounds is not a lot of money, because we are talking about budgets of tens or even hundreds of millions per hospital. So if you invest once every 5 years in a computer cluster, it's not that expensive. It's not prohibitively expensive, let's say. Your advice on STEM, studying STEM, near STEM background, studying STEM programs. I'm not sure I understand this question. What does near STEM background means? I have a generic advice to everybody who is targeting STEM or wants to be involved in STEM. You have a choice of many different subjects. You can do many different subjects in high school, and etc. The bit that everybody is looking at, first and foremost, is mathematics. And there is a reason for that. I mean, we have seen that people that can do mathematics can also do many other things, where people who cannot do mathematics at a certain level may have a problem, you know, dealing with other subjects. So the one thing that I have to advise is don't drop your mathematics. Try to do well in your maths, both as far as admission to university, which of course is important, but also as far as your life in university. If you have a solid, strong mathematical background, you are going to find at least the first year and probably beyond in university less challenging, even if you end up in really challenging subjects, okay? How is computer modeling made to show the simulations? Is it based on tests done? So what the computer that does simulations produces is numbers, nothing but numbers. It creates the simulations I'm discussing, give you a coordinate in space, x, y, z, a time, t equals 0.7 seconds, 3 velocities, u, v, w, and a pressure. And it does that for, let's say, 1 million different coordinates in space when we cut down our vasculature in little small bits. From that point on, the simulation bit is over, and you go into graphics and scientific visualization. We are very fortunate these days that we don't have to reinvent the wheel as far as this is concerned, because there is really excellent software for scientific visualization that is freely available. 2 of the very best pieces of software, one is called ParaView and the other one is called Visit. They are really outstanding in terms of quality of graphics, the versatility, what you can plot, how you can plot it, and they are free. They are open source software. So when you go to that level, it is good. We are in a good place. Rose is telling us that we are going to take one more question only, the last question, as she calls it, and we're going to conclude after that. And the last question is more personal. What attracted you most about engineering? So thank you for that question. It is I'm going to say something that's very personal here. For me, engineering is basically very close to applied physics. It is physics with a purpose. We are trying to understand physical processes, and when I say physical, I mean it in the most broad sense. It might be physical, it might be chemical, it might be biochemical, biological. Everything is dependent on laws of physics. And then the difference is that we're trying to do something about it. So that is the big thing about engineering, that we are trying to convert that understanding into something that changes things in our everyday life, for the betterment of everyday life, and in this case, for the betterment of the life of patients and doctors to a certain extent, because it can be really stressful not to have the tools that you want in order to treat something. So what attracted me the most to engineering was exactly that, the fact that it combines this level that satisfies my curiosity. How do things work? How do if I push this lever and I do that, what's going to happen? Combines that with the urge to try to do something about it, as I call it, to try to improve things, try to make them better for everybody. I hope everybody enjoyed the talk, that you had a good time. And I don't know if there's anything more to say on my behalf, Rosie. Thank you for your attention. Thanks for being here. It's been really a pleasure.
And a huge thank you to you, Yiannis, for that. That was a really interesting talk. And thank you as well to all the participants who asked it really interesting questions as well. In the chat, I've just dropped a link to the rest of the lectures that are part of the series, so you can have a look and see if there's any you would like to join. If you're specifically interested in mechanical engineering, then we have one this Friday about looking into additive manufacturing and 3D printing. I've also popped a link in there to a feedback survey, which is just if you have any thoughts, and just so that when we run this series again, hopefully next year, maybe even with some of it in person, we can improve on it, and that your feedback would be really appreciated. That is everything from us. Thank you again for coming along. It's been so interesting, and it's really great to get to interact with prospective, current, and any other students who might be in the participants. Thank you again, Yiannis, as well.
Thanks, everybody. Really a pleasure. Take care.
Thank you.
Bye-bye.